So in order to get this concept, the best thing is to work out a problem. In FEM, this becomes quite handy when you really work out a problem, then you really absorb the concepts that you learn. So let's try to get together and, of course, work out a problem. Let's go through step number 5, so that we try to consider the element stiffness matrices which we obtain for beam elements to obtain, let's try to assemble them and to obtain global equations and also introduce the boundary conditions. And for this, we will use this example. We can use this figure, which shows a beam which has been fixed at one end. On the left hand side, it has been fixed, and on the right hand side, it has been supported by a pin. We call it a pin supported boundary condition, and we assume that the modulus of elasticity and the moment of inertia on the z axis along the beam to be constant. Yeah, so this beam we can define using, let's say, two nodal coordinate systems. In this case, since the global coordinate system coincide with the local coordinate system, we can simply take out the x hat term and use x and y. And we see that the beam has been subjected to a force in the middle, as well as a moment of 1,000 pounds pound-feet in the middle. So it is important to denote a node at the middle. Yeah, so we define this total beam using 3 nodes, 1, 2, and 3, and we consider it to have 2 elements, the first element and the second element each having a length L. So if you know these boundary conditions, let's say, now try to obtain the element stiffness matrix. So how are we going to tackle this problem? We write down the element stiffness matrix for each element. So element 1 and element 2, based on the derivation, based on the equation which we just derived, which is nothing but this equation number 13. This is the element stiffness matrix for a beam element. So based on this, what you do is simply you write down the element stiffness matrix for element 1. Of course, you know the form of the element stiffness matrix because we just derived it. And on the top, you can denote the degrees of freedom, nodal degrees of freedom. And for element 1 and element 2, if you have written, you can check that the element stiffness matrices should have this form given by equation A and equation B. Now, the next thing is nothing new. Using these element stiffness matrices, you can use the direct stiffness method to construct the global total stiffness matrix. Since the local coordinate system and the global coordinate system coincide with each other, we can skip using the hat symbols because there's no rotation in this case. Of course, we can simply skip these hat symbols and directly use the symbols without the hat sign. And interestingly, we have done nothing new. Write the global coordinate systems, and using the direct stiffness method, you can construct the global stiffness matrix using equation A and B. Yeah, so what you would end up here, of course, in the global stiffness matrix, each node has 2 degrees of freedom. So altogether there will be 6 degrees of freedom. We can write d1y. If we consider node 1 is d1y and phi1, the transverse displacement and rotation. Similarly, the transverse displacement and rotation, node 2, and similarly at node 3, transverse displacement and rotation 3. in this. Yeah, so you can pick out the corresponding terms, and by applying the superpositioning method, you can construct. Here also you can see the degrees of freedom which I have written on top of each element. So based on this information, you can construct the total global stiffness matrix for the total beam considering the 3 nodes. And of course, now you can write it using the nodal degrees of freedom and relate it to the applied external forces on the system. So what are the boundary conditions that we know that we can apply? We know at node 1 it is fixed, and at node 2 it is a hinge or it is pin supported. So at node 1 it is fixed, means the transverse displacement in y direction is 0, and since it is fixed, we assume that there can be no rotation also at node 1. And what is the boundary condition at node 3? Since it is pin supported, it is it cannot move. It cannot have a transverse displacement in the y direction. Yeah. So let's try to denote this. At node 1, it is fixed, no rotation, no transverse displacement. At node 3, it is spin supported, no transverse displacement. These are the boundary conditions. You apply these boundary conditions in this equation C, and you try to reduce the equations, or only take the corresponding matrices, the none where you had to multiply by 9 zero values. So you simply skip out phi 1, d1y, and d3y, and of course reduce the equations by obtaining considering these degrees of freedom at node number 2, and as well as the rotation at node number 3, and apply the corresponding boundary conditions. Here the force, the moment, the force negative because it is acting in the negative direction based on our sign convention. The moment is positive because it is in the anticlockwise direction. And of course here at node number 3, we know it is, since it is been supported, we know the bending moment is 0 because it's free to move. Based on this, when you solve this equation, which it is up to you to solve, you can find the corresponding nodal degrees of freedom at node number 2, that is the transverse displacement, the rotation at node number 2, and the rotation at node number 3. Yeah. So by applying these boundary conditions. So this is something up to you to solve. So now, since we have already laid the foundation, let's use this concept and try to analyze different equations. Let's say analyze certain problems, or let's try to use this this method and apply this direct stiffness method to analyze certain problems considering beams, so that you get familiarized with different aspects. So let's try an example which we can use to which we can apply the theory or the element stiffness matrix which we derived to access get the answer for a propped cantilever beam. Yeah, so let's try to use this direct stiffness method and analyze this propped cantilever, which is subjected to a load P at the end, and it has been propped, roller supported at the middle, and has been fixed at node number 3, that is at the end. And assume that it has a constant EI, that is modulus of elasticity, and the moment of inertia around the z-axis, and the total length of the beam is 2L. So the beam is propped at the middle. You are supposed to find, okay, the nodal displacements wherever possible or wherever is required. In this case, the nodal displacements at node number, of course, 1. the rotations, the reactions, the shear force, as well as the bending moment diagram for this problem. Yeah. So interestingly, the first thing we can do is using the element stiffness matrix for a beam element, or I have shown here for the beam element stiffness matrix for beam element. You have to write down the element stiffness matrix for element number 1 and element number 2 separately and assemble them to get the total global stiffness matrix equation. So this is nothing but the same concept which we apply over and over again for different elements. Okay, so I'm not devoting a lot of time because you are already familiar with this concept now. Yes, so you can use the global stiffness matrix which you derive for a beam element, apply uh, it for the element number 1 and element number 2 uh, to construct. I will not write down, let's say, uh, the element stiffness matrices separately because you're already familiar with this. When you work out on your own, you can do it and check whether you get this answer. So if you have done your math correctly, this is the element stiffness matrix, the global total stiffness matrix which you get after assembling, considering the nodal degrees of freedom at node number 1, node number 2, and node number 3. And you would end up in getting a symmetric matrix like this. Once you get the symmetric matrix, you need to relate it to the, let's say, applied forces and of course the nodal degrees of freedom. So what are the boundary conditions that we need to apply? Here we know at node number 2, since it is propped or since it is pin supported, there's no deformation, transverse displacement in the y direction. At node number 3, we know it's fixed, so the rotation and as well as transverse displacements are zero. And since d2y, d3y, these things are these boundary conditions are zero, you can see partition the relevant equations, that is equation number, the corresponding equations would be, you can see, you can partition the relevant equations here, where the non-negative terms appear in order to get the solutions. 1, 2, of course, the fourth equation, you can partition, the remaining equations are also zero. So once you partition these set of equations, you would end up in getting a matrix, which is given by this. So this is a partition of this total matrix, okay? Such that once you take all the terms corresponding to zero values, you would end up, or you would get a submatrix. You call it a partition. You have partitioned the matrix so that you use the first, second, as well as fourth equation, first, second, and fourth equation, which I have just written here, to partition, and you have partitioned the relevant matrices based on the corresponding non-zero terms. So by solving this partition matrix, you can obtain, let's say, by applying the boundary conditions, you can obtain the transverse displacement and obtain a nice, let's say, equation which describes the transverse displacement at node number 1, and of course the slopes at node number 1. So in this case, you have obtained, let's say we will obtain a negative sign, negative transverse displacement at node number 1, meaning the displacement will occur in the negative y direction, and the rotations you would get to be positive, meaning they are acting in the counterclockwise direction at node number 1 and node number 2. You may see now you have been able to get relationship for rotations using, let's say, these physical parameters as well as the applied load of the propped cantilever. So the next task is, since you already know these unknown degrees of freedom, in order to find the global, let's say, forces and moments, we back substitute them back into this equation number 2. This total, the huge matrix, we substitute all the unknowns which we obtained now into this equation number 2, to solve, to obtain, let's say, unknown forces and of course nodal moments. So once you back substitute, of course, these are the values that we just found. These are the boundary conditions which we applied. Once you solve these equations, which I encourage you to do it on your own, you would end up in getting values for the displacement transfers, or the forces acting at node number 1, 2, and 3, and the corresponding moments at different locations. So since we know that we have got, let's say, if we back substitute all these values, we will get, this is again to check whether we have got the correct answers. You get a minus p value at node number 1, which is correct, which is the applied nodal force in the opposite y direction, and F2y, F3y, and so M3 can be considered as the reactions by the supports which the beam is experiencing. Yeah, so M1 and M2 are 0 because there are no applied or reactive moments present at these locations. So this is the physical interpretation of the results that we have just obtained. So in certain cases, you may need to do somewhat in-depth analysis and try to acquire results of specific elements. Now, assume that you're not interested in the total structure, but you're interested in a particular element. Let's say if this beam the beam contains, let's say, 2 elements, one made using a weaker material and one made with an harder material. In finite element simulations, also in your lab classes, you will do this. Whenever there are complex geometries, you want to see whether this material will fail, or what are the critical conditions you need to consider when you're designing an optimized solution for a particular problem. So in that case, you need to analyze element by element. Yeah. So for example, in this case, let's assume we need to access the forces and moments of element 1. So to check, so that we check whether we are in the safe region or not. Okay. So what you do is, in that case, you simply extract the element stiffness matrix for a particular element and relate it to the corresponding nodal degrees of freedom. Nothing new. Here I have used the hat sign as well as simple letters, since we already zoom into the element level, where we move into the local coordinate system as well as the local forces acting within an element. So same process can be used to analyze element number 2, which I will not describe. So what you would end up, if you analyze these 2 elements separately, you would get results which I have shown here. So I have simply worked this out and shown the results here. So you can work it out on your own and try to see whether you get these results. So at node number 1, at an element level, these are the forces acting. At node number 2, the element level, these are the forces acting. Yeah. Similarly, for node element number 1, element 2, you can obtain the results, and you can plot these results using free body diagrams for element number 1 and element number 2. Here I have shown element number 1. This is the element number 2. And once you access, if I just write the forces, yeah, F1y hat, of course, the M1 hat, if this is node number 2, let's say, is that the case? How we found? Yeah, node number 1, 2, and 3. At node number 2, we have F2y hat, M2 hat. This is, of course, element considering element 1. Similarly, you can consider element number 2 here, which I have shown here. F2y hat, element number 2, M2, element number 2, and F3y hat, element number 2, M3 hat, element number 2. So once you write down element level equation, you can find the values for F1 hat, M1 hat. Likewise, all the nodal forces as well as moments acting at each node. And here I have represented them using free body diagram. And now my attempt is to draw, let's say, the total. Of course, if you move from the left hand side, if you consider the total forces applied, yeah, you have a negative force applied at, let's say, node number 1. And when we move on up to node number, at node number 2, we encounter 2 forces. At if we consider element 1, there's a positive force applying in the y direction, and of course there's another. If you consider element number 2, elemental equations, of course there you will find that F2y corresponding to second element will be 3p times 2. So at node number 2, you then have to sum them up. Yeah. At node number 3, again, you only have this force acting in the negative y direction. So similarly, you can basically, this is a shear force diagram. Starts from minus p value and increase up to 5p times 2. And of course, throughout the rest of the beam, you the result would be, of course, the shear force would be 3p times 2 until the end of the third node, the shear force diagram, which I have drawn here. So similarly, you can draw the bending moment diagram for these two elements. If we consider the bending moment, since we know at node number 1 there is no bending moment involved. Since it's free to rotate, and at node number 2 it increases up to minus pl by 2, because here you can see there's no bending moment applied at node number 1 of element number 1. Then in the middle at node number 2, you can see moment is applied in the clockwise direction, and in the clockwise direction pl, and there's another one acting in the anti-clockwise direction, which is given by pl by 2 in the opposite direction. So these two, when you move on from node number 1 to node number 2, you can see from the there's no bending moment initially, and the total bending moment and the second location becomes PL by 2. And when it comes to the node number 3, again, you end up in getting a nodal bending moment to be equals to PL by 2 at the very end of node number 3. This is just for you to see. Even I mean, if you now take the second derivatives of this shear force diagrams and of course the third derivatives of bending moment diagram, you would see that you would get the corresponding relationships which we just described previously. So what I wanted to say here is that you can still use bending moment diagrams as well as shear force diagrams to analyze what really happens along the beam, since you develop also this theory based on the shear deformations as well as bending deformations. So it's nothing new.